Hi guys, in the last short video I discussed with you isolated version of the switching power supply topology, which is called the forward converter. And in forward converter we saw that the energy is transferred instantly. I mean, when the primary winding is conducting, the same extent as secondary winding is conducting and the power is transferred to the output. And we also saw that in the forward converter the primary winding is conducting only for less than 50% or close to 50% duty ratio, and for the remaining time the reset winding conducts, so that the flux is restored to its initial position and the saturation of the transformer doesn't occur. In today's short video, I will discuss with you another switching power supply topology, which is also the isolated version. I mean, the transformer is used in between primary and secondary side, so the isolation is created, and this topology is called the push-pull converter. In push-pull converter, there are two primary windings instead of a single primary winding of the forward converter, just we saw in the forward converter. And these two primary windings creates a seesaw effect, as we see seesaw in the playgrounds. I mean, on the both ends of the primary winding there are MOSFETs or transistors connected to them, and the middle point is connected to the input DC voltage, rectified DC voltage. So when one MOSFET conduct, the other side of MOSFET doesn't conduct, and when other side of MOSFET conduct, then the on the other side MOSFET doesn't conduct. So this in this way the primary winding conducts half of the time. Each primary winding conducts half of the time, or a maximum of 50% duty ratio, and the power is delivered to the output. When one side of the primary winding conducts, the flux builds up on one side of the direction, and when the other primary winding conducts, their flux is restored to its initial position. Before discussing the flux imbalance, as I told you in the forward converter that normally there should not be any flux inside the core, because when primary winding conducts, the flux is created in one direction, and when secondary winding conduct, instantly the flux is generated in a reverse direction due to Lenz's law, and so the flux cancellation occurs and the net flux is zero. But due to impedance of the primary winding, as it is operating at high frequency, there is a current that passes through the primary winding. This is called the magnetizing current, and this magnetizing current has nothing to do with the secondary winding. So due to seesaw effect in push-pull transformer, when one side of MOSFET conduct, that side of primary winding builds up the this flux due to the magnetizing current in one direction, and when the other side MOSFET conduct on the other side of the primary winding, that flux moves back down, so that the flux is stored to its initial position. However, due to differences in the on times of the boss MOSFETs, the flux can staircase in one direction and ultimately can saturate the core. For example, suppose that we are using the BJT transistor to switch the primary windings. BJT, bipolar junction transistors, has inherent storage times. I mean, when this there is a turn of command given to the base of the BJT, then still there is a delay in the command to be effective, and so that transistor gets turned off. This delay creates a difference in the on time of the both transistors, and so the flux can staircase in one direction and ultimately can saturate the core and destroy the power supply. So to cater these problems of flux imbalance, there are some remedies that should be done. For example, instead of a VGT, we can use the MOSFETs, and because there is no storage time in the MOSFETs, so they act instantly. And there is also an advantage of using the MOSFET, that as the current increases in the MOSFET due to staircasing of the flux, that increased current creates a voltage drop on the MOSFET, and that voltage drop on the MOSFET, increased voltage drop in the MOSFET, drops the voltage across that side of the primary winding, hence the saturation doesn't occur. Another way to avoid this flux imbalance and saturation of the core is to slightly gap the two sides of the ferrite cores. The purpose of gapping the ferrite core is not to store the energy, as we saw in the flyback converter. We saw in flyback converter that the gap is created to store the energy, so that this energy is transferred to the output side when the secondary winding is conducting. The purpose here is to increase the current scaling, so that a large amount of current can be accommodated without saturating the transformer. Another way to avoid the flux imbalance is to use the current mode topology. Before 2 decades, the push-pull converter was very popular, but normally 2-3 decades ago, only the voltage mode control was possible. And when the current mode control came into existence, it monitors the cycle by cycle current of each MOSFET, and decreases the on time of that side of MOSFET if the current is increased, so that that decreased command of the on time decrease the current through the MOSFET, and so saturation doesn't occur. So we can use the current mode the controller ICs to avoid the flux imbalance. Push-pull converters normally can deliver power a maximum of 500 watt. However, push-pull converter has some disadvantage, that the leakage spikes on the primary side transistors is very high, and the voltage stress is also more than doubled. And voltage stress on the MOSFET is double that of the rectified primary side of voltage, and on that double impact of voltage, there is 30% another voltage due to leakage inductance. There is the spikes due to the leakage inductance. So the push-pull converters is not popular in today's power supplies. Instead, if we need more power and we want to avoid the leakage spikes, high voltage leakage spikes, or the high voltage on the primary side MOSFET or transistor, we use some other topologies of the isolated version, which will be discussed later on. So in push-pull converter, we saw that it is also just like the forward converter. The power is delivered instantly to the output side. However, there is a flux imbalance problem that can be created due to differences in the volt seconds of the both side of the MOSFET, which are acting as a seesaw. So that flux imbalance can saturate the core and destroy the power supply and the MOSFETs. So and we saw that the push pull converter can deliver a maximum of 500 watts, and but there are some other power supply which are more popular than the push pull converter. And if you want to use the push pull converter in today's world, then we have to use the current mode topology to avoid the flux imbalance problem at all. This was today's short video. So stay connected, and thank you very much.